So welcome back again to this class. We were discussing about combinational circuits, in that specifically full adder. In last class, we come to know if we have two 4-bit numbers like AND and added, and how input carry, then sum, and then output carries are coming into picture. This we come to know through this 4-bit parallel adder. So in this full adder circuit, we know it can be realized using two half adders and one OR gate. So this is a full adder. In full adder, we have three inputs. So these are the three inputs and two outputs. One is sum and another one is carry, and so on. For 4-bit, we need four full adder circuit. So now, once we know this, how to realize a digital circuit on a hardware, how to do this arithmetic operation. Now coming on this carry propagation. Carry propagation, this section deals with the issues occurring in carry. So if you can see, this is figure 4.10. It tells about this full adder with P and G shown. Okay, so we know this is full adder. Entire circuit is called full adder. In full adder, we have three inputs: AI, BI, CI. These are the three inputs, and we have two outputs: SI, that is the sum, and this is a CI plus 1, that is the carry, next carry. This is the previous carry, or say present carry. This will be next carry. So some generic name is given like PI, GI in between, and then here uh, PI exclusive OR of CI, which is here third, second bit, second input. However, from where this is CI. Okay, then using this external gate, external OR gate plus two half adders, we can realize full adder circuit. Now, what is the issue basically? Issue is like this. Suppose two 4-bit number is there, A0, A1, A2, A3. This is AI. Then BI is B0, B1, B2, B3. And you add. So in hardware, what is going on? Basically, at the same time, we have these two inputs. But while calculating the answer, you can see the output, first output, this least significant bit will be here, some 0, then carry will be here, then here some 1, then carry will be here, then some 3, so sorry, some 2, then carry will be here, C1, C2, C3, and some 3, and then carry 4. So what is going on? You observe that this output will immediately available as 0 as soon as inputs is available. However, S1 is available till C1 is calculated. Similarly, S2 is only calculated till C2 is available. Similarly, S3 is available unless C3 is calculated, and lastly C4. Then only the solution is complete. So what we are observing that? We are observing that this carry propagation, carry C1, C2, C3, it has to generate it in order to get the sum. And since this becomes a serial process, and in that you can see here two AND gates are in process, at least in one full adder. So this is the carry which I am talking about, and it is generated by passing these two NAND gates, this and two, this one and this one. Then only at the summation, because this then only we can get the final carry. So because of that, the entire process becomes very much delayed. Okay, so your process of calculating sum is delayed. So this is what is mentioned here. If you can see, the signal from the input carry Ci to the output carry Ci plus 1 propagates through an AND gate and OR gate, which constitute two gates level. If there are four full adders in the circuit or in the adder, the output carry C4 would have 2 multiplied by 4 into 8 gates level from C0 to C4. For an n-bit adder, there are 2 multiplied by n gates level for the carry to propagate from input to output. And that is the issue that makes your circuit uh, slower. So the carry propagation time is an important attribute of the adder because it limits the speed with which two numbers are added. Although the adder, or for that matter any combinatorial circuit, will always have some value at its output terminal, the output will not be correct unless the signals are given enough time to propagate through the gates connected from the input to output. So, in order to deal with, we we increase the circuit complexity and decrease this propagation delay time. So you can see here, I will show first final circuit so that you should have idea what is our objective or what is our target, so that intermediate path you can follow. So you see this is adder, half adder you can say, and this is the final sum output from another exclusive OR gate. So you can see two exclusive OR gates are essential to get this sum. Similarly for next bit, next higher bit, this is the this and this, next this and this and this. However, in this box, what is that circuit? In this box, the circuit is here, 4.11. 4.11 is an extra circuit designed to take care of carry propagation. So you can see it is two level implementation. Two level means first level is this and second level is this. However, in absence of that, whatever earlier circuit we were having, it was having four levels. Four level means total eight gates. Four level means total 8 gates are coming. Now from from 4 level to 2 level we have reduced. And two level is reasonably decreases the propagation delay time. But how to design this in order to reduce the propagation delay time? That is our next issue. So how to design this circuit? What is the logic behind designing this circuit? Let us try to understand how to design a carry propagation or carry look at circuit generator. So this is the circuit. It start from the given circuit, that is the full adder, and we give the name Pi, which is the output of this exclusive OR gate, and Gi, which is the output of say carry. First and second one, Pi exclusive OR of Ci, which is obviously here, and then last one is here, Pi Ci plus. Let me remove this so that you should know. So Pi Ci, how? Because this is here, Pi from here and Ci from here. So this is the one output. Another one is this one. No, second one is here, sorry. Second one is Gi. This is not coming here. This one. Gi. So Pi Ci plus Gi, which gives you the next carry, Ci plus 1. Is it okay? Now let us see how it is going when we apply I is equal to 0, 1, 2, 3. So Pi is equal to Ai exclusive OR of Bi, means first number and second number. And Gi, which is the intermediate one, is equal to Ai Pi. This is given in your here. You can see Pi is nothing but Ai exclusive OR of Bi. And Gi is Ai Bi. And logic. And this final sum S is equal to Pi and Ci. This is written here. And Ci plus 1 is equal to GI plus PI CI. I think this is the equation which we are getting from the figure 4.10. Now you give this I is equal to 0, 1, 2, 3. Okay. So GI is called carry generate, and it produces a carry of 1 when both AI and BI are 1, regardless of the input carry CI. PI is called carry propagate. So carry generate is a PI, and carry propagate, and carry generate is this GI. Now, see for I is equal to 0, if I is equal to 0, so C0 will be input carry, and most of the time input carry is 0. And Ci will be, if I is equal to 1, that is Ci is equal to G0 plus, no, for I is equal to 0 only we are getting this. Okay. And for I is equal to 1, Ci plus 1, I plus 1. This is the thing now. You remember? To put I is equal to 0, 1, 2, and 3, like that. So you will get this one. So C2, I is equal to 1 here. I is equal to 1, then it will be C2. Is it okay? And here, G1 plus P1, C1. And now this this P1, C1 can be written in terms of C1 can be written in terms of G0 plus P0, C0, this one. So we expand this one. In nutshell, what I'm trying to tell that higher, higher order terms are expressed in lower order terms. Okay, like C3 is expressed in terms of, look here, C0 is the first carry, even initial carry, then P0, P1, and P2. This is the C3. Okay, and we can realize the circuit according to this expression. One can try to write this expression by their own pen pencil, so that one should understand. Otherwise, it is difficult to say in wordings. Main equation is this one. Which one? This SI plus 1. So should I write here? Ci plus 1 is equal to GI plus PI CI. So if I is equal to 0, so C1 will be Z0 plus P0 C0. Is it okay? Now, if I is equal to 1, if I is equal to 1, then it will be C2, then here G1 plus P1, C1. And now the C1 is already we got from here. So put the value of C1 here and expand. Okay. Then I is equal to 2. Then we will get here C2. So we can write here, it is 2, G2 plus P2, C2. And C2 already will be C2, yeah. C2 can be written in terms of previous expressions. So this is how it is written here. And then you implement C1, C2, and C3 with the help of two-level logic implementation. And after that, we put back again your earlier circuit, this one, and the final circuit, this one. And in between, we have that look ahead carry generator. This is called popularly as look ahead carry generator. So what is ultimate aim? What is the purpose? Why we are doing this? Just to decrease the propagation delay time taken by carry generator. Why? Because it is taking 4 into 2, 8 gates level. Okay, or 4 level, but through 8 gates. Now it is only two level implementation means two level implementation gate, okay, or 2 gates simply. So in this way we are able to reduce the propagation delay time. Any question, class? And how we are able to do? By increasing the circuit complexity. By increasing the circuit complexity, we are able to minimize the propagation delay time. But there is a cost. This is what we are trying to tell here. Circuit complexity. We have increased the circuit complexity compared to earlier in order to gain the in order to make the circuit faster. That was the issue. Any question? In chat box also no question. Now coming to binary subtractor, next topic. So we are familiar with this circuit. For time being, we forget this one. Exclusive OR one. So A0, B0, just give directly A1, B1, A2, B2, A3, B3 and put into full adder circuit. So this is nothing but 4-bit parallel adder. However, if we, however, in order to do the operation of adder as well as subtractor with the help of same circuit. This circuit is basically adder because full adder is used here. So this is adder. However, this is amp. Amp is your control line. If amp is equal to 0, then circuit will be your adder. Circuit will work as a full 4-bit parallel adder. If m is equal to 1, circuit will work as a 4-bit subtractor. Let us verify whether it is correct or not. By law, why I am telling that if m is equal to 0 and m is equal to 1. It may be reverse also. Let us check. So, how can I check? I can check like this. This is the exclusive OR gate. Let me write the truth table of exclusive OR gate 0 0 0 1 1 0 1 1. And output of exclusive OR gate is 0 1 1 0. Is it correct? Everyone knows this now? Yes or no? कोई बोले तो सही.
Yes, sir.
Very good. Thank you. So from here, just give observation. If this is exclusive OR gate, let me use red pen only. If I make one of the logic is 0, okay, permanently, and now I put say here A, what will be the output? Look here. If A is equal to 0, let me see, this should be B, not A. If A is equal to 0 for this case, then what is the output? Output is nothing but B. B is 0, so Y is also 0. B is 1, Y is equal to also 1. So Y is equal to B here. Okay? Take another case. If A is equal to 1, now instead of making 0, I make it 1. Then what will happen? Output is B complement. How? Because B is 0, output is 1. B is 1, output is 0. It means why? Because B complement. B complement. In case if A is 1, is it okay? What in short form I can tell, if exclusive or in exclusive OR gate, one of the input is 0, so it will simply work as a pass gate. However, if it is 1, the circuit or this exclusive OR gate will work as a NOT gate or complement. Is it okay? And now this is what is going on here in this circuit. So you know how we have done the operation of adder with the help of complement method. In complement method, we know that A minus B is equal to A plus complement of B. Yes or no? Anyone can respond. Array.
Yes, sir.
If you
Yes, sir.
recall, A minus B, A minus B. This is positive number. A is positive number, B is also positive number. But operation we are doing here subtraction. This is in binary, this is equal to A plus B complement. This is what we have done with one's complement method. We have done subtraction operation with the help of adder operator with the help of using uh, one's complement method. Okay. And now we want to get this complement, and complement can be generated with the help of not get. And this is M. If M is connected here, M is connected here, M is connected here, and M is connected here, that is the one of the input of exclusive OR gate. So if M is equal to 0, this B0 will simply pass here, B1 will simply pass here, B2 will pass here, B3 will pass here, and entire circuit will work as a adder. However, if M is equal to 1, then exclusive OR gate will work as a NOT gate, and at the output here, at the output of exclusive OR gate, you will get B complement, that is B0 complement, B1 complement, B2 complement, B3 complement. And the adder will work as a adder only. What is that? A plus B complement. And A plus B complement is nothing but the subtraction operation. So this is how we can do the subtraction operation or subtractor design of subtractor circuit with the help of adder. Only we have added this exclusive OR gate. And logic behind is this one. With the control of M, if M is equal to 0, entire circuit will work as a adder. If M is equal to 1, entire circuit will work as a subtractor. And this is taking care of overflow V. Okay. If both are 1 1, this one, either of this will be 1, either C or C4, then output will be 1, otherwise 0. Then only you will get the overflow. Overflow is an extra output which is not uh, accommodated in the circuit, which is given here. Okay, this decimal adder is not in your circuit syllabus. How? Let me see BCD adder. I can explain, no problem. No, it is not in syllabus. What happened? Why is so slow? Binary multiplier is also not in syllabus. Magnitude comparator is there. I will cover this one also. Not get. Okay. Magnitude comparator basically is a comparator which compares magnitude of two binary numbers. Suppose number A and B. We have two number A and another number is B. If we compare these two, what may be the possible output? Possible output may be three. Three possible output may be there. One is that A is equal to B. Another one is that A is greater than B. And third one may be A less than B. So A is greater than B, A is equal to B, and A less than B. These are the possible outcomes in a magnitude comparator. Input is A and B, two numbers are there, and outputs are three. Okay. So whenever any circuit we are going to design, we should know how many inputs are there, how many outputs are there, and what is the relationship between input and output. Then accordingly we can make the circuit. Now take this example. Number A and number B, two numbers are there. A is equal to A is written as 4-bit number A0, A1, A2, A3. B is written B0, B1, B2, B3. Okay. Now, when two numbers are equal, when A is equal to B, what is the condition? How we will take the decision that A is equal to B? The simple thing which we know that we compare bit by bit and starting from the MSB, that is the most significant bit. If A3 is equal to B3 and A2 is equal to B2 and A1 is equal to B1 and A0 is equal to B0. Then only A is equal to B. This is the foremost important criteria for, for declaring two numbers are equal. I think sounds sensible. Any doubt?
No, sir.
No, sir.
So, but this logic can be implemented with the help of which gate? Exclusive NOR gate. Look here, A is equal to A and B, 0, 0, 0, 1, 1, 0, 1, 1. I want to write the truth table of exclusive NOR gate. Earlier I was writing exclusive OR gate. That is called XOR gate. XOR gate truth table is there. Earlier I wrote no. Oh, I can write here, no problem. Can write again. XOR gate was A B Y 0 0 0 1 1 0 1 1, and it was like 0 1 1 0. XOR gate is just reverse of this because one NOT gate is put. So 1 0 0 1. Okay. What is conclusion? After observing, if you observe it nicely, you will find that when A and B are 0 0 or 1 1, then it gives logic 1. Okay. It means if A is equal to B, then Y is equal to 1. It means this this checks equality. This checks equality condition, which exclusive NOR gate. So with the help of exclusive NOR gate, we can implement this logic. A is equal to B. If output of exclusive NOR gate is equal to 1, it means the output is equal to both number are equal. A and B are equal. So this is what is written here. And we know the Boolean expression of exclusive NOR. Xi here I subscript is given, I is equal to 0 1 2 3 AI Bi plus Ki complement Bi complement. I think sounds sensible. Since this we have considered for 4 bit, so we need suppose A0 is equal to B0, then output will be X0. A1 is equal to B1, then output will be X1. A2 is equal to B2, that it will be X2, and output will be X3 when fourth bits are equal. Is it okay? Here you can see this one. So A and B, A0, B0 is equal to then X0, A1, B1, X1, A2, B2, X2, A3, B3, X3. Okay. And in between, among them, there is an AND gate. Means exclusive NOR gate. Here again, exclusive NOR gate, exclusive NOR gate, exclusive NOR gate. And all are added and given to AND gate. And this will give you A is equal to B. And what are here? Here we have A0, B0. This one will be A1, B1, and so on. So this way we can realize this logic with the help of exclusive NOR gate and AND gate. So this is the one third circuit of entire magnitude comparator. Got it?
Yes,
Yes,
sir.
sir.
We have realized one third part. That is the simplest one is the A is equal to B. But there may be issue of A is equal to B or A less than B. How can we realize the circuit? Go by logic. Suppose A is greater than B. This condition, this is possible when A3 is 1 and B3 is 0. Isn't it? Suppose I write here number A0, A1, A2, A3 and B0, B1, B2, B3. I want to compare. I have to compare. I have to start comparing from MSB only. Okay, this is what we do. Like 5,100, and another number is that 4,999. So how can we compare? Means what is the strategy? We start comparing from this MSB, isn't it? We do not start comparing from LSB, is it? When we compare, just immediately if we see that this is 5 and this is 4, so we take the decision 5 is greater than 4, so obviously rest number is smaller than this one. Although this is 100 and here it is 999, still since MSB is lesser than this MSB, that is why that number is lesser than first one. Second number is lesser than the first number. So same logic is applied here. A3, B3. If this condition is satisfied, then we can say A is greater than B. If this condition is not satisfied, hello, yes, anyone wants to speak? If both are same, like this 5 is here, 5 is here, then what we will go? We go for the next number. It means both are same. Both are same is taken care by x3. X3 tells that the MSB is equal in both A and B. Then we have to check for A2, B2 bar. Okay, A2 should be 1 and B2 bar is this is 0. If this is the case, then A is equal to B. If this is also not the case, then we go for third case. That is the, it means here why we have reached here, because first MSB and second MSB both are same. Then we check for next bit. If this is also same, then we go for the last one. So x3, x2, x1, a0, b0. You see, this is a OR gate. So either of one condition will satisfy to make a is greater than b. Okay. Now, if we further extend this logic for a is less than b, just make it reverse. Or for circuit implementation point of view, what I used to suggest implement this logic first one, and just suppose I got this logic from one of the OR gate. We have this circuit. So what I used to do, I put a NOT gate here, and this is telling A is greater than B, and here A is less than B. Why? Because if A is not greater than B, then obviously A is less than B, isn't it? So NOT gate will serve instead of implementing the entire circuit separately. However, since it is given in book and we want to understand the logic, so either of these two is possible. You implement A is less than B, and then take complement output for A is greater than B, or you implement A is greater than B, take the complement of that one and get the A is less than B. Now let us see. Okay, just since we are studying first time, so let me elaborate second one. And there is error, which typographic error. We have to remove this. So A is less than B is possible when A 3 bar B 3. Okay. Next, if A3 B3 both are equal, means X3 is there, then A2 bar B2, then only B is greater than A. If this is also not the case, then here X3, X2, A1 bar, B2 bar is B1 bar is written, which is wrong. It should be B1 simply. Is it? Can you see?
Yes, sir.
I will make it bigger a little bit. So in your book, you can make it correction. So it will be A1, okay, plus X3, X2, X1, and then A0, this is not this one, A0 bar, and this will be simply B0, not bar, okay. Then only A is less than B or B is greater than A, okay. Now after that, Once we know the logic of this A is equal to B, A is less than B, so we can realize no need to copy this circuit. I would not suggest to copy the circuit. You realize the circuit from here. Okay, the way I told, you take four inputs like this A, A3, A2, A1, A0, and here B3, B2, B1, B0. Okay, and put not gate also here so that you can get the complement. And after that, realize this circuit, this one and this one. Okay, these x3 are coming from here like x0, x1, x2, x3. Okay, and try to implement circuit from your own logic instead of just copying from this book. Okay, if you will copy that, you may there is a probability of committing the errors. So I will not suggest to go for it. You realize your own circuit. Okay, once we understand the logic. Any question till now with this?
No, sir.
No, sir.
Okay.
Yeah.
Now coming on this decoder. Next, this is again another combination circuits, which is by definition, if you go a decoder is a combination circuit that converts binary information from an input lines to a maximum 2 to power n unique output lines. This is the definition. A decoder is there. Suppose this is block diagram. We have an input and bit input. So output will be 2 to power n. Suppose 3-bit input. So how many outputs will be? 8. If 2-bit input is there, how many output is there? 4. If 4-bit input is there, how many output lines? 16. Okay. So this is the simple thing. Suppose I write here 2-bit. So output will be 4. Okay. This is what is the meaning of our definition. Decoder is a combination circuit that converts binary information from n input lines to a maximum of, this is written maximum of, it may be less than also, maximum of 2 to power n unique. These all outputs are unique. Okay, unique output lines. If the n-bit coded information has unusual combination, some combinations are not used, then unused combination, the decoder may have fewer than 2 to power n. So this may be less also. Okay, let us see this circuit. We have started from 3 input line, not 2 to 4 line. Okay, no problem. Okay, so input lines are here X, Y, Z. This is 3-bit input. Yes or no?
Yes, sir.
Yes, sir.
X, Y, Z. And if we write like this 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. These are the possible combinations with the help of 3-bit. Okay, so this is 3-bit, and these are the outputs. How many outputs are there? Total 8 outputs. Okay, and 8 outputs are written here: D0, D1, D2, D3, D4, D5, D6, D7. And you see, first output is nothing but X bar, Y bar, Z bar, which is written here. Second one is there X bar, Y bar, Z. This is here X bar, Y bar, Z. Third one is X bar, Y, Z bar, X, Y, Z bar. And we have to just only take these outputs from this AND gate. Okay. So you can realize this the circuit this way. However, I used to do like this. I will write here. My way of writing is little bit different. क्यों नहीं काम करता जल्दी जल्दी? As I have done earlier also, I will show you once, then another one you can do in expanded form. So here I have line x. Oh, x, and I will take here x bar. Okay, then y, and this will be y bar, and here z, and another one will be z bar. So x bar, y bar, z bar. And if I want to take this one, this is a simple. You can suppose I want to implement first one. So I take this and get and put x bar, y bar, z bar. Okay. Similarly, you can go for this one, D1 here. So in this way, we are able to realize this circuit. And this circuit is nothing but 3 to 8 line decoder. Simple. Any problem? You can see D7 is nothing but X bar, X, Y, Z. So it is given here. Uh, First line is connected to with what? Z. This is the Z. That second one may be X, and this one Y. Actually, this way, sometimes it becomes confusing. For me, it is easier like this to check any connection. Okay, and this is the truth table. Truth table of 3 to 8 line decoder. So X, Y, Z, all combinations right from 0 to 7. That is 111. And you can see D0 is giving output 1 when first case is there. D1 is the output 1 when X bar, Y bar, Z is there. D2 is what when X, Y, X bar, Y, Z, and like that. So you can see these are the unique outputs. Others are 0. So this is how 3 to 8 line decoders are implemented. So this is the truth table of the circuit, above circuit. A decoder is used for implementing this logic. We will see how we can implement full adder circuit, half adder circuit with the help of decoder. Now, another circuit 2 to 4 line decoder with enable input. So what is it? In order to control entire circuit in one switch, that is called enable. So, but to get the enable circuit, we have to use this NAND gate, because NAND gate has very good property that just see here A, B, and Y. 0 0 0 1 1 0 1 1. So any 0 makes output 1 and 0. So you see, it can be any 0 makes in the input, any 0 available in the input makes the output of an NAND gate 1. However, if both inputs are 1 1, then output is 0. So this is the property. Now whatever input is there, X and Y, if this enable line is 1, if this enable line is 1, here 1, what will happen? Here you will get 0. And this 0 makes of all NAND gate is equal to 1. Is it? It means this is not as such working. There is no as such information. So this is how we are able to control it, irrespective of whatever is this one. So that is why if NAND gate is there, in simple logic, we used to tell that f is equal to 1. Wherever f is equal to 1, you have information. Now, if we are implementing with the help of NAND gate, we tell that wherever logic is 0, f is equal to 0, at that time you have information. Okay, that gives reverse logic. So please keep it to mind. Now let us check. If enable is 1, irrespective of A and B, whether it is 0 or 1, it doesn't matter. It means the circuit is disabled and all gates are giving 1, 1, 1. It means it is not as such functional. It is disabled as such. Now, if E is 0, then based on this A and B, you will get the output. E is 0, suppose all 4 cases, it means the circuit is enabled, circuit is functional. Now based on that input, like A is 0, B is 0, you will see D is 0. It means this is the output. However, others are 1, 1, 1. That is the unique output. Next is, if next case may be 0, 1. At that time, this D1 is giving the output, negative output. Okay, and others are 1, 1, 1. Third case, 1, 0. Second, this D1 is output, giving the output. And fourth case, this should be 1. It is wrongly written here. Okay, this should be here 0. D3. Okay, so in this way, logic 0 means negative logic is giving as a output of the function. So 2 to 4 line decoder, because we have 2 input lines, and is equal to 2, and output line will be 4. 2 to power n is equal to 2 to power 2 is equal to 4. Any question?
No, sir.
No, sir.
Okay, thank you. Now this figure tells about how can we realize 4 cross 16 means 4 input is equal to 4 bit, and output will be obviously 2 to power 4 is equal to 16. But issue is that we don't have circuit, we don't have decoder of 2 to 4, 2 to 16, sorry, 4 cross 16 decoder. We have this circuit, 3 to 8 line decoder, 3 to 8 line decoder. Okay, it can be realized simply like this also. This box is there. You give here 4 to 16, 4 input line, 1, 2, 3, 4, and 16 output lines. There is no issue. That can be easily implemented. But if this IC is not available and you have this IC, 3 to 8 line decoder, but 2 in numbers, then is it possible to realize higher order decoder with the help of two lower order decoder? Yes, this is what it is speaking here. What is the logic behind it? You can see from here. W, X, Y, Z. If we write this number, so it starts from 0, 0, 0, goes 0, 1, 1, 1. What is this number? It starts from 0 to 7. Okay, it means first 8 number. And after that, what will happen? After that, it will be 1. Then again start from 0, 0, 0. Then 1 will be 0, 0, 1. So you see, this number is repeated. 0 to 7 is repeated for next 8 times. But W is 0 for first 8 and W is 1 for next 8. So this is what logic has been used here. If W is 0, it means first half of 3 to 8 line decoder is working and you will get this output. If W is what? That is that from 10 to 15, then lower 3 to 8 line decoder is functional and giving the output D8 to D7. So with the help of this NOT gate, one extra NOT gate and 3 to 8 line decoder, we are able to implement 4 to 16 line decoder. Got it? So lower order decoder has been used to implement higher order circuit. So that is the beauty, or that is the feature of this circuit. That is why it is given here. So in digital electronics, for that sake, we more emphasize on the logic. With the help of logic, we can realize complicated circuit with the help of simpler circuit. Okay, and in this way we get the benefit out of it. Otherwise, by definition, we can implement this one also, 4 cross 16. But if we have 3 cross 8, 2 3 cross 8 and one not gate, we can realize this circuit. Okay. Now, yeah, very good. So now this is what I was trying to tell. Why why we are studying this decoder? Decoder can be used to implement circuit. What kind of circuit? The simpler circuit is the full adder. We know the output of full adder, one is the sum, another one is the carry. And sum from the two table, sum is equal to 1 at bit term 1, 2, 4, 7. And carry is equal to what at 3, 5, 6, 7. This we know. If you want to extract, I can tell again. I can write here again. Sum and carry. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So sum will be here 0, carry 0, sum will be 1, carry 0, sum will be 1, carry 0. So carry will 1, sum will be 0, 1, 0, 1, 0, 1, 0, 1, 1. So this sum, this is S, is 1 at what place? 1, 2, 4, 7. This is what is written here. 1, 2, 4, 7. And carry is 1 at 3, 5, 6, 7. So this is 3, 5, 6, 7. At these places, C is equal to 1. Is it okay? Are you
Yes, sir.
following?
Yes, sir.
Yes, sir.
Very good. So you people are convinced that S is equal to summation 1 2 4 7 and C is equal to 3 5 6 7. Now how to realize with this circuit full adder with the help of decoder. So in decoder we know all AND logics are available. D0, D1, D2, D3, D4, D5, D6, D7. We can see here first one. This circuit is nothing but here. Okay, in the box, whatever you have seen, this is the circuit. Okay,
Yes, sir.
so in this 3 to 8 line decoder is given, and this is D0, D1, D2, D3, D4, D5, D6, D7. Same circuit. This circuit is given in now in a box. This one. Okay, and now here X, Y, and Z. So Z is the least significant bit. That is why 2 to power 0, 2 to power 1, and 2 to power 2. And after that, we know sum is equal to from this D1, D2, 1, 2, 4, and 7. From there, you give the connection to OR gate, external OR gate, and you will get the output of sum. Similarly, for carry, you need only to connect from 3, 5, 6, 7. So this is 3, this is 5, this is 6, and this is 7. And you put one OR gate because AND logic is available here. AND A and T. AND logic is available here. You need only OR logic to implement from the external gates. So you see as many as function you can implement with the help of external OR gate. So some suppose you want to implement subtractor also here. So write down the expression of subtractor here. So subtractor we have difference and borrow, isn't it? So what is the expression of difference? You write here. What is the expression of borrow? We write here and put one OR gate here for difference, one OR gate for borrow, and do the connection here. You will able to implement the subtractor here. So full subtractor, full adder with the help of 3 to 8 line decoder and few external gates. So this is the advantage. So no need to realize this inside circuit because it is ready-made available, this one. Okay. So this is one thing. Sometimes we used to tell that realize full adder or half adder with the help of 3 to 8 line decoder and NAND gate. Okay. NAND gate and A and T NAND gate and A and T gate. So instead of OR gate, in this case, we are realizing OR gate, but if I tell use NAND gate. So at that time, what you have to do, this logic which are available here, now it should be NAND gate here. Another first one you have seen here, this This is the output of NAND gate. No? So this we have to show here in the diagram, in the block diagram, NAND gate. And after that, same thing you can do for NAND, put here NAND gate. And so 1, 2, 4, and 7. This will be sum. And put here NAND gate for carry to what is this output? 3, 5, 6, 7. So you can give here 3, 5, 6, 7. So in this way, with the help of 3 to 8 line decoder plus NAND gate, we can implement. Okay. So with this, thank you. I conclude this class. Up to decoder only we can cover in our midterm exam. And one more thing I would like to tell you that in your Morris notebook, let me show you 3.9 section. That will be assignment. Of course, you will submit that later on, not now. To do VHDL simulation. Okay, you have to write the code, and how to write the code, it is given in book. However, you have to, once we understand the basics, then we can understand, we can go for complex circuit. Yeah. Can you see section 3.9? Anyone respond?
Yes, sir.
Yes, sir.
Yes,
So
sir.
this is hardware description language, HDL. HDL. Hardware description language. This coding is used for circuit implementation in digital logic. Okay. So first, I would like to tell, suppose this circuit is given, this simple circuit in which we have a AND gate, we have OR gate, and we have NOT gate. So 3 input lines and 2 output lines, D and E. Is it okay? And
Sir.
one wire line is defined. How to write a code? How to write a HDL code of this given circuit? This is a kind of language. No? We are through language we speak. How to, because suppose this circuit is not able, machine is not able to understand. Of course, so what we have to do? We have to communicate with the machine. So machine understand the language that is called HDL code. So how to write this same circuit in using code? This is given here. I will tell you. So the entire circuit start from the module. Okay, the keyword called module. Okay, Yara. This bold letter is module. It is not sensing. Which problem? Can you hear me?
Yes, sir.
Yes, sir.
My pen is not working. Yeah, it is working now. So start from the module. Okay, that is the keyword. Then after that, you have to write the name of the circuit. Suppose here the name of the circuit they have given simple circuit, simple underscore circuit, and then within the bracket, that is the argument, we have to define input and output. So A, B, C, you can see these are the input, and D, E is the output. Then once it is written in argument, now specify or declare as output. Output is a keyword, then D, E, semicolon. These are the output, two outputs of the circuit. Then input ABC, input keyword, and then ABC. And there is one intermediate wire. Okay, W1, that is the wire. And after that, this AND is nothing but logical AND. This gate G1. So G1 is written here within bracket. So we have to write here what is the output, first output, and then the input. So AB is the input and W1 is the output. So this is what is the way. This is the way through which we write this logic. So and then second one is the NOT. So add A and D is nothing but your capital A and D in logic. Okay, In the script, we write like that. Not gate, NOT, and OR gate with the help of only OR. So G2, this is the second gate, is E is the output, which is here, and input is C. Simple. And then after that, OR, third one, this OR. OR output is D, we write here D, and inputs are W1 and E, which is the output of this NOT gate. And after that, AND module. So module is the starting and AND module and end. So entire circuit is written in this form. Okay, this is SDL code. You can read this description. And in next one, we need to declare the timing also. Okay, and after that, we need test batch in order to give all kind of inputs and get the output. Okay, so in the table they are realizing logic. Suppose first input is 0 0 0. After that they are giving 1 1 1. So what shall be the output when input is given 0 0 0, and after some time they are giving 1 1 1? So what shall be the output of the circuit? So this is the basic things in this circuit here, which is given here. So first A, B, C is 0 0 0. So what is the output? D and E. And then another case is 1 1 1. Then what is the output of D and E? This is the thing. For that they have written a code, but here we need some delay. Is how much time each gate takes. That is the propagation delay time, which is mentioned here. So like AND gate is taking 3 nanosecond, sorry, 30 nanosecond, NOT gate is 10 nanosecond, and OR gate is taking 20 nanosecond. And this is the test batch, which test all, which gives the stimulus to the circuit. Okay, and after that, this is the wave shape. So this today I just want to give you introduction to this HDL. Further, you have to see this is an extra work. It is not as such given in your curriculum. But from my side, I will consider it as an assignment. 50% will be your mid semester and 50% shall be this. And there is a website called EDA Playground. On EDA Playground platform, select that Verilog platform and write this code and simulate it. Okay. And I will give you flexibility. Student can choose of their odd circuit. Odd circuit means as per their liking. Liking means if you choose complex circuit, obviously you will put hard work. If somebody is not enough acquainted or not ready to give hard work, can select the simpler circuit. But this assessment will be accordingly. Okay, so if you want to higher marks, you have to go for the you have to increase the difficulty level of the circuit. Okay, so it depends on one's capability. So that kind of autonomy I am leaving on you. Is it okay? However, I will ensure to give minimum marks to each, at least passing. I'm not going to fail. Okay.
Okay,
But
sir.
but
Yes, sir.
in order to get good marks, you have to do little bit hard work. So that will be submitted at the end. But today onwards, you try to give some attention on this also. That assignment will be this much only. Syllabus, whatever circuit we are teaching you like decoder, you can write the code for decoder, okay, in SDL and implement on software. So there you have to also write the test batch as well as the code. So that can be a assignment, and accordingly you will be given the marks.
Sir,
Okay,
one code for each, like
one code for
one
each
code or
means
circuit. We can choose either one, but we have to do only one from each, like any one.
one student will submit only one, but please ensure that you should submit your best one. For exercise purpose you can do anything, but for assessment purpose you submit your best one, because this will carry your marks.
Okay, sir.
Is that it?
Okay, so good.
So you do the practice. I will share the link also here. This EDA playground, you can write it to Google, and you will get that. And that is browse based platform. So you need not to download EDA playground. That you have to select your code. I think on some YouTube they have given what is called process. Some of volunteers. EDA playground. So this is the website. Okay, you have to open through your Google account or Facebook account, or you can register and write the code. Okay, and simulate from there, and try to learn, because it should be easier for you people being in the laptop IT department. Okay,
Clear.
chalo. And for mid-semester exam, you will have this up to decoder. Okay, whatever we have covered today till today, because your exam will be on Thursday.
11.
Yeah, Thursday, 11. And today is Friday. Okay, ठीक है. चलो, bye. Thank you for attending
Thank you,
the
sir.
class.
Thank
Thank
you,
you, sir.
sir.
Thank you, sir.
Thank you.